Processing heavy local AI data pipelines requires forcing massive amount of dense unstructured information through strict unyielding mechanical bottlenecks. In phase 4, our objective is exactly this. We must convert time-stamped English JSON transcripts into regional Indian languages, outputting accurate synchronized SRT files. The primary tool for this task is AI for Bharat's IndicTrans2, utilizing their 200 million parameter distilled model assessed via the IndicTrans toolkit. This introduces a structural tension. Our existing audio extraction pipeline operates natively on Windows, but the Indic translation toolkit is optimized exclusively for Linux. Forcing Linux native AI tools onto a Windows host results in persistent build failures. To maintain production stability, we must design a hybrid architecture. Attempting to compile incompatible Linux libraries directly on Windows inevitably breaks pristine Python environments. Instead, we deploy WSL2 Ubuntu as a designated safe sandbox to execute the translation toolchain. This architecture allows us to pass lightweight text data across the operating system boundary without duplicating massive media datasets on the drive. The Windows side handles all creative and input-output tasks. The Linux side acts strictly as a remote computational engine. Treating the OS boundary as an intentional filter protects the integrity of the audio pipeline while allowing the AI models to operate in their native environment. This diagram shows our shared drive strategy. Windows Drive D is accessed directly by WSL2 through the mount mnt/d/mounting point. Pipeline text files like our JSON inputs and SRT outputs cross the bridge seamlessly. But if we allow the Hugging Face model cache to be stored on the shared Windows NTFS drive, the system stalls out. Linux file system mechanics rely heavily on symlinks and cache metadata. When these operations are forced onto an NTFS mount, performance degrades and the file locking errors occur. We solve this by setting the HF home environment variable, ensuring the model cache is isolated strictly within the WSL native home directory. Separating shared I/O data from isolated model caching ensures the Linux tools run at full speed without file permission conflicts. Our first execution hurdle is access. Hugging Face gates the download of the 200 million parameter IndicTrans2 model. We clear this by generating a read token on the platform and authenticating the command line interface using HF Hub login. This dependency tree maps the toolkit. When we initiate the translation script, we immediately hit a module not found error. Newer Hugging Face releases have completely removed the legacy.onx export modules that the IndicTrans toolkit requires to run. We fixed this by executing a strict environment rollback, pinning the transformers library exactly to version 4.4.2. This reveals a second failure, an import error specifically targeting PreTrainedTokenizerBase. We resolve it by applying a structural patch directly to the toolkit's local files, manually editing the import path from tokenization utilities to tokenization utilities base. Rigorous version locking and localized package surgery keep the pipeline operational despite shifting open source dependencies. With the environment stable, the Python script extracts the text strings from the phase 3 English JSON. This visualization compares local video RAM capacities. Passing pre-processed text batches into the seek-to-seek model requires strict memory limits. For an RTX 5070 Ti, a batch size of 8 provides optimal throughput for the distilled 200 million parameter model. On an RTX 4060, pushing 8 blocks triggers a CUDA out-of-memory error. Lowering the batch size to 4 ensures the GPU completes the task safely. The Indic processor formats the batch and passes it to the generate function, utilizing float 16 precision to conserve memory. Finally, the script decodes the generated tokens, maps them back to the original timestamps, and uses the Python SRT library to write the export file. Precise hardware-matched batching guarantees a crash-free local translation loop. Our English to Hindi architecture now acts as a stable baseline to successfully reach all 22 scheduled Indian languages. Expanding the pipeline to Kannada, Tamil or Telugu requires zero structural changes to the environment. This grid maps the language to their syntax codes. Swapping the TGT_lang parameter to a target like can-knda instantly redirects the translation output to Kannada. To translate directly between regional languages, we swap in the Indic-to-Indic 320 million parameter model, allowing us to route Kannada to Hindi without referencing English. The hybrid architecture processes all of these complex permutations flawlessly without requiring a single adjustment to the underlying WSL2 sandbox. By locking down our Hugging Face dependencies and leveraging the OS boundary to handle caching, we have built a stable, scalable translation engine. This output is the exact required input for phase 5, where we are going to generate naturally sounding audio in local Indian languages.